If Intel says that we are coming up with a new microprocessor of 18 nanometer technology, that means this channel length, this distance between drain and source is 18 nanometer. If they said we are moving to 5 nanometer, that means they're talking about this dimension, the distance between the drain region and the source region. This purple area, the length from here to here, right under the blue gate oxide, that is called the channel. The length of the channel area defines the technology. So earlier at the beginning of integrated circuit or transistor era, this length of the channel, these were in the range of tens of micrometers. That means 10,000 or more nanometers. Gradually, process improved, the dimension shrank, and now we are talking about in the order of tens of nanometer. 18 nanometer is in commercial production. So, as a whole, in the MOSFET transistor, there are three material components. The top one is metal or any conducting material layer. Current days we use polymerized silicon, polycrystallized silicon, which acts like a conducting metal. The second layer of the MOSFET structure field is insulating oxide, and the bottom layer is, hey, how are you?
Good, how are you?
Good to see you.
Good to see you.
So this is the bottom layer, that is the silicon layer. The reason this device, just a quick recap for those who have not taken my VLSI class. The reason this device is called MOSFET transistor, it is a field effect transistor, that's why it's FET. But why MOS? Metal, oxide, semiconductor. Conducting layer, metal, insulating oxide, and semiconducting silicon layer. So, all the microelectronic applications as of now, this base layer, this semiconducting layer, is made of silicon as a material. Why they choose silicon? Because this is most widely available semiconductor in the world and very cheap. So if you separate oxygen from sand, sand is silicon dioxide, then you get silicon. So it is, the raw material is free. You can collect sand from any sea beach or any desert. You separate oxygen from silicon dioxide, you get silicon. So that's why abundance of material is important. There are metal semiconductor, but we never used it for commercial large scale production because those are rare. So, when we talk about moving from micro scale to nano scale, so there are lots of dimensions. One dimension is thickness of the silicon layer, width of the entire silicon layer, thickness of this oxide, width of this gate or channel. So all these dimensions at the beginning of IC era were in the range of tens of micrometers. Now all these dimensions are shrinking down to nanometer scale. Among all the dimensions, most important dimension is the length of the channel, the distance between drain and the source terminal. This length of the channel, this dimension defines the technology. So, what is happening as we are shrinking? All the dimensions are shrinking. Along with those dimensions, the thickness of the silicon dioxide is also shrinking. Now it reaches at such a level that, now let us look at the material. The material of this insulating oxide or gate oxide is commonly used silicon dioxide. Silicon dioxide, so why silicon dioxide? Because the bottom layer, semiconductor layer is silicon. So material compatibility wise, it is better to put something made of silicon so it bonds well. So silicon dioxide is an insulator, silicon is a semiconductor. Now, for conducting metallic layer, earlier they used aluminum or copper, but now they are used polycrystalline silicon. Again, why? Silicon dioxide, polycrystalline silicon. 3 layers of different types of silicon composite. They bond with each other. So why it is polycrystalline? Because polycrystalline silicon gives the same property as a conducting metal. So for material compatibility and ease of manufacturing, they use all silicon composite in current process. So among these dimensions, the smallest dimension in the entire MOSFET transistor is the thickness of this oxide layer. And that oxide layer is made of silicon dioxide. So as we are shrinking all the transistor dimension, this oxide thickness came down to only 2 nanometer. Before we move to the consequence of reaching 2 nanometer thickness of silicon dioxide, first let us ask a question: why we are shrinking all the dimension? What is the motivation? Why we cannot keep it at 10 micrometer? Why we have to bring it down to 10 nanometer? From 10 nanometer to 10 micrometer to 10 nanometer, that means we shrank the dimension by 1000, right? So the question is why we have to shrink it continuously. Now Global Foundry, Intel and Samsung, they're talking about 5 nanometer. Why we're shrinking? The answer is, you and I, we want to do more with our laptop, cell phone and tablets. That means we want more signal to be processed at a much faster time, at a much lower energy consumption. So our cell phone is full of thousands of apps. We are running parallelly. Behind the scene, even if your cell phone is off, it is actually running on the background many apps. So whenever you are running any apps or doing anything, any computation, any calculation, picture taking, video taking, behind the scene, at the chip level, at the microprocessor level, what you are doing? You are processing billions of electrical signals, binary signals. And to process those signals, you need transistors. More work you want to get out of your devices, that means you need to process more electrical signal and you need more transistor. One transistor can handle only one electrical signal at a time. So if you want to run many more parallel application, that means you need to have many more transistors parallelly available to work to process all those signals. So now the real estate space where your microprocessor or any chip should be fabricated, that real estate space remained constant for the last 70 years. It is 3 centimeter by 3 centimeter max. Typically it is 2 by 3 centimeter. So between minimum 6 to maximum 9 centimeter square, that is the space you have, size of a silicon chip. So within 6 to 9 square centimeter space, only way you can put more transistor to do more function is to reduce their size, minimize their size. That's why from the beginning of IC era till today, the size of transistor went down by 10,000-fold. From 10,000 micrometer to nearly 5 micrometer. So, along this dimension shrinking, one dimension is most affected, the smallest dimension, oxide thickness, silicon dioxide. Because silicon dioxide is made of one silicon atom, 2 oxygen atom. Together, when you put this one silicon atom and 2 oxygen atom together in a chemical bond to form one molecule of silicon dioxide, these 3 atoms together will have a certain height, right? These are physical atoms. If you keep shrinking, you cannot go below 1 atom. You cannot go below 1 molecule. So, you cannot expect that one molecular layer of silicon dioxide can form a physically stable silicon dioxide. You have to have at least 5 to 10 molecules sitting on top of each other to constitute a reasonably stable oxide layer. So that's why, and those 10 silicon dioxide molecules on top of each other, we have to see what is the dimension. Physicists must tell us what is the minimum number of molecules stacked on top of each other can give us a physically stable layer that can be recognized as a silicon dioxide layer. Then we have to see if it is 10, what is the minimum height of those 10 molecules stacked on top of each other. That means the thickness of oxide cannot go below that. If we go below that, then this layer will not physically exist. Then the device will cease to exist. So there is a scaling dimension. So that the question is, as we want to do more work at a faster rate, we want to shrink the size in every dimension, and we want to also run them faster. One of the ways to run them faster at lower energy consumption is to shrink this layer, bring the gate layer closer to the channel, so that the signal from drain to source can run faster. One of the way to make the speed of the transistor faster is to bring the metal gate closer to the semiconductor channel. How can we bring it closer? By shrinking the thickness of the gate oxide. But we just said that there is a minimum limit up down to which we can go, then beyond that we cannot reduce the thickness of silicon dioxide. So at the nano scale, and then also even when we reach minimum thickness of gate oxide, minimum dimension in every possible direction, this semiconductor, which is silicon, it has a limit for a given voltage, how much current it can deliver. But the work at one point in future we want to perform may need more current for the given voltage applied at the gate. That means silicon will not be able to provide the level of current at much lower voltage needed for the function you want to perform. So people are looking for alternative to silicon. And then silicon dioxide reaches a minimum thickness limit. Beyond that, it cannot provide any further improvement. So people are looking for alternative to silicon dioxide to further shrink it, or even for the same dimension to get more current. And people are also simultaneously looking for new gate material. So research and innovation from micro scale to nano scale to sub-nano scales are going in multiple fronts. One front is looking for new material. The other front is changing the whole physics. This is based on field effect transistor principle. The question is whether the physics of field effect transistor will be sufficient in future to satisfy our demand for higher performance at lower energy. The answer is no. The field effect transistor has a theoretical performance limit. Beyond that, it cannot provide any more performance improvement. So people are looking for new physics, new ways of implementing transistor for signal processing. So invention is going in two different directions. Changing the basic physics of the transistor, moving away from field effect transistor, or at the same time looking for new material for field effect transistor and the newer physics or technologies. So in this lecture we are going to look at mostly both material as well as transistor physics principle. Yes.
So how close are we to realizing this limitation with our current technology that's being built? So it's currently around like 1.7 or 1.4 nanometers.
So they're expecting that for the channel dimension, probably for silicon in the conventional bulk MOSFET actually is not working below 20 nanometer. They already moved to FinFET. It is still a field effect transistor, but they are no longer using this type of bulk. We will see all those device structure. Intel already moved to FinFET for 18 nanometer. So this structure is kind of no longer valid at high frequency. For low frequency is okay, but extremely high frequency, Intel already moved to FinFET. And all the other companies, they already are moving to FinFET. But they're now saying that FinFET will not be enough. So the next stage is still FET, below 1 nanometer or around 1 nanometer dimension. It will be nano air FET. And nano air FET also will reach, ultimately, as long as we remain within the realm of field effect transistor FET, there is a limit. That's called Boltzmann tyranny. We cannot reach that. So probably 20, 30 years from now, we will move to some other newer technology. But to answer your question, for very high frequency application, this is called bulk MOSFET structure. It is already has become obsolete or is becoming obsolete at 18 nanometer and beyond. For 18 nanometer channel size, this thickness is around 1.7 to 2 nanometer. So, what are the different issues with this planar or bulk MOSFET technology? So one of the main issues is that increase in leakage. Leakage is a huge problem for smaller dimension device. There are many different types of leakages, at least 3 types of leakages we have discussed in previous course, but those who have not taken Introduction to VLSI class, just quick recap. What is leakage? Leakage is the unwanted current that is flowing through the device or through the circuit when your system is supposed to be in off condition. That means when you are not doing anything, there should not be any current going from source to drain or this way or that way or from gate to channel or source to body. Right? So let me summarize the operation of the transistor a little bit for quick recap. A transistor, MOSFET transistor, has 4 regions or 4 terminals. Gate terminal, source and drain, and the body. Body area or this terminal, this blue region is the body, and a terminal coming out of that body region is called body terminal. This region is called source, the terminal is called source terminal, this region is drain, it is called drain terminal, and this is gate terminal. Gate is separated from the body by an oxide. So a transistor should send current only from source to drain when the transistor is turned on. When the transistor is off, there should not be any current going from source to drain. And at any condition, on and off condition, no current should go from source to body, drain to body. No current should flow from gate to source or gate to drain because it should be insulated. So the current in a transistor in ideal state should only flow between source to drain only in on state. Current should not flow between source to drain in off state, and current should not flow between source body, drain body, or gate source drain at any condition or off condition. But practically, there will be some current going from source to body, some current going from drain to body, some current going from source to gate, gate to drain. And in the off state, when no current should flow from source to drain, there will be some small amount of current in the on state, in the off state going from source to drain. So those all are unwanted current. And those unwanted current are called leakage. They are just draining your battery, not actually doing anything. So the leakage is the number one threat for energy efficiency, indirectly longevity of your battery in any micro or nano electronic system. And with the shrinking of this dimension of transistor, all the different leakage components become more and more prominent, stronger compared to the current you use during the on state, right? So, from any transistor, you have one current you want to be as high as possible. That current is the on state current from source to drain. You want that current to be as high as possible so you can do more work at a faster speed. More current means signal will travel at higher speed, right? So there is wanted current, on current from source to drain. Everything else, off current from source to drain, and all the current between source, body, drain, gate, terminal, those are all unwanted current. Those are leakage of state current. So one of the quality measure for any transistor is the ratio between on current to off current. Larger the ratio, your device quality is better, because that means your on state current is much stronger and larger than your unwanted leakage or off state current. If that ratio becomes closer to 1, that means you are wasting more current in the off state than your on state when you're actually using your device. So off state current increases with the shrinking of the device dimension in bulk MOSFET. So that's why in the current bulk MOSFET technology, below 100 nanometer size, majority of the battery's energy you are storing in your cell phone or tablet or laptop, a majority of them are wasted as a leakage or wastage throughout the system before even it reaches the microprocessor to do the actual work. So that is one of the biggest threat, the off-state energy loss or system loss in micro scale or in sub-micro scale. So, and one of the leakage current component is called drain-induced variability, DIVL. Drain-induced variability, what does it mean? When we turn on the transistor, by applying a voltage at the gate, a channel is formed, and then we apply a voltage between source and the drain, current starts flowing from source to drain. With the increase of drain voltage, more and more current will flow. So that is expected. In the on state, more voltage we apply here, more current we should expect, and that current will be the useful current to do all the function or the signal processing you want to do. But one of the problem is, with the increase of drain current, the channel itself gets distorted. It becomes shorter and shorter. When channel becomes distorted and shorter, it affects an important parameter of the transistor that is called threshold voltage. or the barrier voltage. If the barrier voltage changes, transistors off-on characteristics will change. Also, with the change of barrier voltage, one of the main component of leakage current or off current will increase exponentially. If the threshold voltage of the transistor or the barrier voltage of the transistor is decreased, one of the component, the largest component of I-off or leakage current will increase exponentially. So we are increasing the drain voltage to get more current, but an indirect consequence of that increased drain voltage is lowering the barrier potential or the threshold voltage of the transistor, which affecting the magnitude of the leakage current. And that effect is more predominant in smaller and smaller device. So this is becoming an issue for short channel device. What is a short channel device? Now let us do the definition. Let's go back to the previous slide. In general, transistors are divided into two groups: long channel device and short channel device. Device means transistor. Long channel transistor, short channel transistor. Now, is there any division? Okay, up to this dimension we will call it long channel, or up to this dimension, below this, no. It's just a relative terminology. So in a transistor, there are many geometric dimensions. Thickness of the whole silicon layer, thickness of the source and drain, width of the source and drain, width of the length of the channel, width of the silicon dioxide, width of the gate, right? So there are lots of dimensions, geometric dimensions you can identify in a transistor. In the earlier version of transistors, MOSFET transistor, length of the channel, the defining characteristics of transistor, was longer than other geometric dimension, relatively speaking. So initial versions of MOSFET transistors were known as long channel transistor. The channel lengths were longer than the channel length, the distance between source and the drain were longer than other geometric dimensions of the MOSFET. So those were known as long channel transistor. But as we are shrinking and shrinking all the dimension, we are shrinking this dimension much faster than any other dimension. So this dimension is becoming equal to or comparable to other dimension, at least some other dimensions of the transistor. So now channel length is no longer the longest dimension or the largest dimension in the transistor. So in the realm, the transistors are now known as short channel device. So short channel device introduces many difficulties, and one of the difficulty is the DIVL, drain induced barrier lowering. The lowering of barrier voltage or threshold voltage due to the increase of voltage at the drain terminal, which leads to much higher leakage. So, and also some other device parameters changes as we move to shorter and shorter channel device. And all those parasitic effects, leakages in short channel device, increased leakages, as a group, it's known as short channel effect. So as the channel length becomes shorter and shorter, some of the material properties of ideal transistor no longer remains ideal. Some of the electrical properties will change, and one of the biggest electrical property change is the increased leakage due to increased DIBL. And all this material and electrical property deterioration as channel becomes shorter is commonly known as short channel effect. So, as a summary of consequences of short channel effect are: you lose the control of the gate terminal. You get more leakages due to short channel effect, especially due to higher DIBL. Now let us look at the first bullet. What do you mean by loss of gate control? So to do that, we have to go back and explain the transistor operation again. How do we turn on this NMOS or in this MOSFET transistor? MOSFET transistor is made of a silicon body, on top of it a source and the drain region. Semiconductor comes in two forms, P-type and N-type. If the body is P-type, source and drain will be both N-type. If the body is N-type, source and drain will be P-type. Under normal condition, transistor, source and the drain is like two isolated islands of N-type or P-type semiconductor surrounded by an opposite type of semiconductor. So there is no electrical path for signal to flow from source to drain. Turning on the transistor means establishing a path from source to drain of the same type of semiconductor. If it is N-type and N-type, I have to establish a path of N-type semiconductor from source to drain. How do we establish that path? By applying an electrical voltage or electrical field on the gate terminal. That electrical voltage connected to the gate exerts an electrical field on this region, and that electrical field, if it is positive electrical field, it forms an N-type channel between N-type source to N-type drain. Why positive field produces an N-type? Because positive attracts negative. So it forms a layer of electron here. So it becomes an N-type channel connecting N-type source to N-type drain. And the transistor has a connection now between source to the drain, and we call it on state. So your ability to turn on the transistor depends on what voltage you apply at the gate. If it is N-type source and N-type drain, you have to apply a positive voltage. It is P-type body and P-type source and P-type drain, you have to apply a negative voltage to form the respective channel here to connect source and the drain. So the polarity of the voltage and the magnitude of the voltage applied at the gate terminal will determine whether you will have a channel between source and the drain, and what would be the strength of that channel, electrical strength of that channel. So the gate is the control terminal which determines whether the transistor will be on or off, a channel will be there or not, and if it is on, how strong the channel is. Strength of the channel means its ability to carry more current or less current. So if the electrical field applied from the gate is much stronger, then it can attract more electrons or positive particles to form the channel. in more electrons in case of n-type source, n-type drain, more positive particles in case of p-type source and p-type drain. Larger the electrical field, stronger the channel will be. Right? So the gate is the control terminal. The operation of the transistor, its ability to turn on and off depends on the electrical field applied from the gate terminal. So, in the short channel device, due to leakage and other effect, gate loses some control on the channel. Here I am just showing source and the drain. Gate is applying the electrical field to establish the channel between source and the drain. As device becomes shorter and shorter, one of the consequences of short channel effect is the control of the gate on the channel becomes weaker and weaker. So, for the same voltage at shorter channel, you will not get a channel at the strength level you expect from that voltage, because gate loses some of its control. So device designers came up with a proposal. Well, in typical planar device, planar transistor, gate sits on top of the transistor and it applies the electrical field from the top of the channel. So they proposed, how about we put a gate at the bottom of the transistor as well, and we apply the electrical field from the both sides on the channel so that the channel forms faster and stronger. And the concept of having two different gates, one at the top of the transistor, one at the bottom of the transistor, this concept has become known as double gate device. So, and to apply the double gate device, the concept is on the top of the device you have a regular gate, and below the body you will have another gate which will be applying electric field in this direction to form the channel faster. But the problem is, so we are going to put a body gate here, right, below. But this is a very, very thick silicon layer compared to this tiny silicon dioxide layer. So the body, the gate that is applied from the bottom, from the body side, to apply force on this channel region, that field will be very, very weak because it is coming from far away compared to this gate, right? So when they introduce the double gate concept, one gate at the top, one gate at the bottom, electric field will be applied from the both sides to form the channel faster and make it stronger. That concept, effectiveness of that concept relied on the fact that they have to make the body very, very thin, so that I can bring the bottom gate much closer to the channel and the field can exert a reasonable force on the channel to be effective. But there are problems. If you make the body too thin, then more unwanted current leakage will go down from source to body terminal, drain to body terminal. You don't want that. You don't know. Ideally, all current should flow from source to drain only in on state. In every other terminal, in every other sequence, there should not be current. As you make the body thinner and thinner, then this barrier will reduce. Some current will leak from source to body, drain to body. So, double gate concept did not work that much. So they tried to bring some modification in the body structure itself, and we'll look into that. So Now that, but double gate theoretically, it will improve transistor performance and reliability. But the initial concept that we will apply the second gate from the bottom of the body, that will not work because the body is at least 100 times larger in dimension than the silicon dioxide on top. That is only 2 nanometer. Body is in like several micrometer, right? So that's why it is not working. But they all agreed that instead of having one field coming from on the top surface, if I can apply more than one electrical field to the channel area from other side, the channel will form faster at much lower voltage and it will be much stronger. So with that concept, device designer kept exploring other structure. Well, planar type, one at the top, one at the below. Then they said, how about the channel which is original bulk MOSFET is horizontal. The channel is horizontal to the device structure. How about we raise the channel like a fin of a fish from the top surface, from its like back, right? So if the channel region rises as a fin above the body area, and if I apply the gate from this side and this side, now I can apply the gate, 2 gates across the channel very close to each other. They will apply very strong electrical field. So I can turn on and off the device with much lower voltage, right? And you will have total control, much stronger control on the channel region from the gate. So here the channel is sitting horizontally between source and the drain. Here I am changing the device structure. It is now a planar silicon coming in the middle and a silicon layer is rising above like a fin at the back of a fish, right? And then you, instead of applying gate from here, you apply gate from this side and this side, like you are sandwiching the channel between 2 layers of gate, gate 1 and gate 2. Both are at equal distance, rightly attached to the channel. You have a 2 nanometer silicon dioxide here, 2 nanometer silicon dioxide here, and 2 different gates at 2 nanometer apart, applying electrical field on this tiny thin channel, so you can turn it on much faster and the channel will be much stronger. Now where do you place the source and drain? If this side and this side, if you make the channel vertical, like rising like a fin, and this side and this surface you are using for applying 2 gates separated by green silicon dioxide layer. But here I connected source horizontally this end and this end of the channel. So they explore 2 different options. Well, vertically, this side source, this side drain. Or source, and one of them can be at the bottom, one of them can be at the, because current will enter the device to the source and leave the device to the drain. We need to have connection between source, channel and the drain to complete the current path, right? Here, source and the drain are placed horizontally at the 2 ends of the channel. Gates are 1 gate only applied. Here, 2 gates are applied from left side and the right side. So the source can be, one possibility can be placed this end, or top end or the bottom end. So they are doing this different structure exploration. Now they are saying that, well, let's put source and drain here. Yes.
So I see that the source and the drain are kind of like smaller than the bulk MOSFET,
Yeah,
because we kind of just went like this and squished it
yeah,
between two gates.
yeah.
And now like the body and the channel, or the green section in the middle,
Yeah.
is that now longer or shorter than the previous? 'Cause
So
we squished
still the channel length is the it is distance between source and the drain. This is the channel length. And this length, so we are just basically, let's say it's a rectangular piece of silicon channel. We are just flipping it like this. So the length is still same length, and this one we are flipping it like this, right? So still source is this end and this end. The question is, we are just flipping it this way or we are flipping it this way. So the channel length still is continuously shrinking. It is now at below 18 nanometer, 10 nanometer now. With FinFET, it is possible to go below because short channel effects are less, because now I can apply the gate at very close on two sides. So then if you think about gate here, gate is applied on the rectangular channel only from the top surface, from 2 nanometer away. 2 nanometer is the silicon dioxide thickness. Now I'm just slicing it, this part, turning it vertically. I'm now applying one gate layer from this side, one gate layer from this side. Both are at 2 nanometer away from the channel, and they are now applying an equal strength field on the channel. So channel strength is becoming almost double theoretically compared to the planar device. Of course, it leads to some processing complexity, but I see manufacturing industry, they have overcome processing challenges. Yes.
Can you go to the previous image?
Yes.
Yeah. Here you can see, normally the channel forms from source to drain in the top part of the near to the gate, right?
Yeah.
So if we apply 2, is there possibility that it can, the channel can be created on both sides of the thing?
No,
Because
the
we are
channel
there to get,
is
right?
always, what do we mean by channel? Channel is the appearance of a connection between source and the drain. So, and there is only one possibility, one connection from this direction, from source to drain. So if you flip it, still there is only one connection from source to drain, one connection from source to drain. So that is actually entire channel area.
So it's gonna nearly double the thing.
Yeah, the only thing changing is the channel is getting 2 electrical field of equal strength. It's like instead of one guy pulling, it's like 2% pulling. So it will basically collect those electron or positive particle much faster to form the channel. Physically, it's one layer of silicon from here to here. This side is doped, either N-type or P-type to make it N-type source. This side is doped, N-type or P-type to make the drain, and this is undoped silicon. With the application of electrical field, we are gathering here electron to make it N-type to form an N-type channel, or to gather positive particle to form a P-type channel. So as they started this structure, double gate, now they're saying that why keep this side left? Why don't we connect this gate layer with this gate layer? So I can apply third component of the gate from the top surface, right? Then they're saying that, well, then why leave the bottom surface? So let's put the gate, let's put the channel fin, surround it with 2 nanometer layer silicon dioxide, and deposit gate metal on all sides and put source and the drain this side and this side. That is called gate all around device. But this rectangular, maintaining proper rectangular shape of the channel and depositing silicon dioxide around that channel and then depositing gate around that channel, in any manufacturing process, when it is running on conveyor belt or spin, it is always easier to make cylindrical shape than rectangular shape. You are processing material at micro and nano scale. So maintaining proper rectangular shape, depositing this tiny layer of material one on top of each other, maintaining this rectangular shape will be much more difficult. But if you do it a wire first, a wire of silicon, and spin it, deposit a layer of silicon dioxide, and then deposit a layer of metal, and then slice it, put source here, drain here, that will be much easier. Because in any automated material processing, material is collected, deposited using some sort of spin. In any spin manufacturing process, when it is spinning, it always forms in cylindrical form. So that they realize that, well, gate all around concept is a brilliant concept. You have a much more control on the channel. You can apply the gate voltage at much from all four directions. So either you can turn on the device at much lower voltage, because now 4 different gate is applying from 4 different directions, or if you keep the voltage same, your gate will carry more current. Your device will carry more current. So the gate all around concept is very novel concept, but maybe the rectangular form is not the best way to go. Maybe cylindrical wire form will be better. That gave to the concept of nanowire device. So the next direction for field effect transistor, right now from bulk MOSFET we move to FinFET. From FinFET, the next logical move will be to nanowire device, which is the cylindrical wire-like implementation of gate all around concept. So that's what we have moved. That is bulk silicon. And then from bulk silicon, as we are shrinking the device, short channel effects is becoming severe, and current should go from source to drain. But when these dimensions are shrinking, bodies are becoming thinner and thinner, unwanted current flowing from source to body, drain to body, which is not contributing to your signal processing. You can use only current that is coming out of drain terminal, that's it. From source to drain, everything else is useless, wastage. But as we are shrinking the device, current will flow from here to here, wasting majority of the current through unwanted path. So IBM about 30 years ago, more than 30 years ago, about 50 years ago, in late early 80s, they came to the concept, and from 90s and onward they implemented it. They said, well, that's fine. Keep the device structure as it is. Let's put a silicon dioxide layer buried beneath the active layer of the transistor, beneath the source channel and the drain. Put a silicon dioxide layer, silicon dioxide is insulated, buried here, so that the body terminal and the rest of the body becomes insulated from the working region of the transistor. So it's a modification of the bulk MOSFET. And that modified device structure was named by IBM as SOI device, silicon on insulator. A layer of silicon placed on top of an insulator layer, to separate it from rest of the bulk of the body, so that no current can flow downward from the drain and source to the body, because it is now electrically isolated by a buried layer of oxide that is called SOI. So MOSFET technology, many commercial application, they still use bulk but in SOI form, right? So the SOI device gave significant improvement, but there was not enough, and they introduced double gate, that another gate buried inside that insulation or below the body. Then they moved to FinFET. From FinFET to, they tried different structure, right? Theoretically, they were improvement over FinFET. FinFET also became known as Tri-Gate, because you have gate this side, and this side, right? Tri-Gate, and then they tried some other structure, but ultimately they think that this will be the cylindrical structure. You will have silicon. First, a cylindrical silicon will be formed, surrounded by a silicon dioxide layer, surrounded by conducting gate layer. Source and drain will be connected from this side and that side. A nanoscale dimension wire formed between a source layer and the drain layer. That wire will act like a channel, and it will be surrounded by silicon dioxide or insulator, followed by a layer of gate. So you will have a total 360-degree application of electrical field on that nanowire size channel. So you will have full control on the channel behavior. Yes.
And this is possible because we're not changing the width of the gate, because we're maintaining the distance between the source and the drain. We're just changing how much of the gate.
No, actually, it is not only we are changing the structure. This type of a structure is also giving us ability to make the channel shorter, and those thickness go down as low as possible. But one of the reasons we are moving to this region, because that silicon dioxide insulation already reached its physical limit. Below 1.6, 1.7 nanometer we cannot go. So that's why we are applying the electrical field from 1.7 to 2 nanometer distance from all direction. So, and gate layer thickness, it doesn't really matter. We can use minimum thickness gate layer, because that is not, gate layer we are just using as an electrical transition point connector. Battery to gate is applying the field on the channel. Important factor is the thickness of the silicon dioxide. How far the gate is from the channel itself. Since that silicon dioxide layer reached its physical limit, we cannot make it thinner anymore. So we cannot make the gate stronger. So instead of from one side, we applied it from 2 sides, 3 sides, now from all sides. So, but within this structure, we can use difference insulation that can even further shrink the dimension. So we will talk about it in the material level. But now that this channel is now in the horizontally, the easier source and the drain, I can bring them closer and closer, because I am not doing anything with the gate thickness or oxide thickness. So I can keep shrinking the channel length without touching the gate layer thickness or silicon dioxide thickness. If the channel length becomes shorter and shorter, I can speed up the operation, and I can put more transistor in the same physical space. So this is the direction of nanowire device. So nanowire device is an active area of research. Many people are working in this area. But before FinFET and nanowire device, one of the important transition from bulk MOSFET is the SOI technology. So SOI technology, we will not actually continue. I have a faculty candidate, so I have a meeting. But we will spend some time on SOI technology because even in FinFET, they use SOI platform. So currently, there are two types of transistors are in use in any commercial ICs. One is bulk MOSFET, one is FinFET. Still, we are far away from commercial use of nanowire. In all commercial digital ICs, either based on bulk MOSFET or FinFET. Bulk MOSFET or FinFET. Both bulk MOSFET and FinFET can be implemented on a bulk body or an SOI body. And many applications, high performance application, they use SOI body. So SOI can be, that body can be used in original bulk silicon MOSFET or in FinFET. And that is kind of de facto standard SOI body in many commercial applications. That's why we need to spend some time understanding what is an SOI technology. Right? So we will start from next Tuesday. So in the meantime, the syllabus is uploaded here. Please download it. All of you have access to Canvas. So where is the syllabus? Yeah, syllabus is, so by next Tuesday, I want each one of you just send me one paragraph that you want to, you don't have to do any research at this point, just I want you to let me know what you want to concentrate on for your term paper research. Just one paragraph, 3-4 sentences. So by next Tuesday. So and this description has other information about different deadlines and grading policy, as well as formatting of the term paper. Okay? So I will continue the lecture next Tuesday, but following Thursday, I want you to just talk 1, 2, 3 minutes about the research topic you want to focus on. Okay? Thank you.
Thank you. Have a nice day.